Alright, so we start again. Yes. So what is this? This is the output of self attention. So which part is done? Self attention layer's output is done. This is what it is. Let's call it S1. Okay. Let's call it S1 1. Why I need this subscript now? Because this is for first encoder. Okay. So first encoder, first unit. Next. What do I do next now? There is a problem here if you see. The problem is I input 512 as X plus positional encodings. I compute QKV, I do all this self attention, and what I get is 64 cross 1, and this is something I don't like. Why? Because the structure says that in this direction dimensions of inputs and outputs, they don't change. So if input to self attention layer was X, which was 512 dimensional thing, output should also be a 512 dimensional thing. How can I make this 512? 64, how can I make 512? Multiply with 8, right? So this is what you do. How do you multiply with 8? How do you multiply with 8? You simply can't multiply by 8. Repeat. So can I repeat this 64 cross 1 8 times? That's also one of the options. Will it be a good idea to repeat? No. Why not? You are just repeating the same information, right? And that's not what you had neural networks for. So what should I do? Padding? Yes, padding is a good option. Can we do something better? So what team at Google did was, look at this carefully again. What does it say? Multi-head attention. So one head gives you 64 cross 1. How many such heads you may have? 8. Okay. So you have 8 heads in the original transformer paper. So these are actually 8 self attention heads. So you have 8 self attention heads. If you go to paper, the variable for that is H. So H is equal to 8 in this case. Okay. So now your output of self attention layer is multi-head self attention layer is done. Okay. 8? That's a good question. How will you do this 8? So I have received 64 cross 1 from one head. So tell me, how did I get this 64 cross 1? These guys, right? So now let me state that this is actually not WK and so on. So this is not WQ, this is WQ1, 1, 1. So how many WQ, WK and WV do you have? 8. So you will have W2, Q, W2, what? K and W2, V, all the way until W8, Q, W8, K, 8, right. 8 and this will be V, right. each one of them will give me phi 1 2 dimensional thing, right. So each one of them will give me phi 1 2 dimensional thing, concatenate them, and what you get is 64 cross 1. Sorry, what you get is phi 1 2 cross 1. And that is actually, so this whole thing is actually S11. Now you tell me. Yes. x1 x2 you have phi 1 2. Yes. See, you have x1 to x phi 1 2. You have these three parameter matrices WQ, WK, WV, right? You know their dimensions now, right? You compute 64 cross 1 for 1. You have 8 such triplets of parameter matrices. Each one of them will give you 64 cross 1. You concatenate. So here this multiplication is basically concat, and you get 64 into 8, which is phi 1 2 cross 1 concatenated. Now let us go back. So this is fine. Now the way they draw this one, again I'll draw what they have in the paper. No, H is a hyperparameter. So how many attention heads you want is a hyperparameter. W's are actually trainable. Hyperparameter is something you don't train, right? That fixes your model architecture. But parameters is something that you train. So WQ, WK, WV, they are parameters, but number of attention heads, they are hyperparameters. Which W's? Right. So this is where we had them. So self attention layer, it takes input x1, then in that self attention layer here, so this is my self attention layer, and all these things are happening inside that, much more than just this, right, because all these computations are also happening here in this self attention layer. So here you have parameter matrix WQ1, WK1, WV1. They give you Q1, K1, V1. Then you compute all the way until this guy, 64 cross 1. Now take, so this one, take another plane at the back of it. So you have kind of 8 depths. So you have 8 depths, each depth doing the same operations, but for second depth you will have different parameter matrices WQ, WK and W. Then for third depth you will have different parameters. Each depth is giving you a vector of size 64 cross 1. There are 8 of them, that gives you phi 1 2 cross 1. So finally what we get is a phi 1 2 cross 1 vector. Okay, and this is the output of what? This is the output of my multi-head self-attention. So we are completely done with the output here, right? Nothing is left here. We are done with the output of this. Add and norm means you right now here you had x's. You have computed the output of this guy, right? Add it to this, so and then normalize. So there are two operations happening here. Add means this x plus output of self attention layer, right? So what add is doing here is, add is basically equal to x plus output of multi-head self attention at encoder 1. You take this whole thing and then you normalize. Okay, you have, so I'll get rid of this guy. No, this is fine. So you have add and norm. What are the dimensions of X? 5 and 2. What are the dimensions of multi-head attention ka output? 5 and 2. You can add them, right, and then you normalize. This output here now, where does it go? See, actually they do one more thing, which is yes. So after concatenation here, okay, what they do is, after concatenation you have S1 of size, you have S1 of size 5 and 2, right. They have another parameter matrix there WO that will take S1 and will give you output. This is that vector which was concatenated, right. So this one. After concat. So after concat, scaled dot product attention, after concat they have a linear, right. This is what that linear is. Give me the dimensions of WO. Dekho, transformer is a big architecture, but it's much simpler than LSTMs, right. There are so many details to it, but it is simpler and intuitive. LSTMs are not intuitive. Yes. What are the dimensions of WO? This has to be 5 and 2 cross 5 and 2, right, because this is the output of your multi-head self attention layer, which then you add and norm. Okay, all right. So we are done with this. Finally, we are done with this part. We are here now. Okay. No. You basically. So we are here. What you are doing is that you are doing layer normalization. You are normalizing that layer to some distribution. In this case, you normalize it to a Gaussian distribution. Yes. So we are here now. What do we do? This part is super easy and we are done with the encoder part in next 5 minutes. So tell me, what is the dimension of my vector at this red spot? 5 and 2. Okay, I have this 5 and 2. What is my FFNN? So FFNN is nothing but this. That's it. Okay. So the output of this add and norm goes in here and then 2048 and then project it back to 5 and 2. You are here now. I don't think I need any explanations here. Okay. You are here now. Add and norm. That same old thing that you did here. And here you have, you keep on doing this for 6 times and finally after 6 encoder layers you will have 3 outputs from here, Q, K and V. I mean you will have actually so you will have outputs there, and now we will see what do we do here. Okay. Questions here? So if you see every k is actually a, how many dimensional thing? Every small k, if I take care of, if I include multi heads, every k is 512, every v is 512, every q is 512. Okay, so I have that. Now what do I do next? This encoder part is done. Any questions? As I said before, transformer is a big architecture. They did so many things in just one paper, and the paper stood the test of time. Even today, when people try to change this relationship, their performance deteriorates, which is, you have this, whatever x it is, you do 4x and then you go to x again. You choose any other number, 2x, 6x, 8x, 16x, that's worse. So the original transformer of doing x to 4x and then 4x to x still works the best. We don't know why, but okay. Yes, any questions in this part? Now we are done with this. Anything that you want to ask? I am not vectorizing this, so you may see that as a very good question for the exam. Okay. Now, yes.
सर जब मल्टी हेड कर रहे हैं तब जो पैरामीटर है क्यू के और पी पे भी कॉन्केटिनेशन हो रहा है.
करा लो, मेरे से ही करा लो सारा है.
सर हो रहा है ना,
हाँ,
जाके वो 5.2 हो रहा है.
exactly. So
ठीक है सर.
So tell me, right now my W1Q is 64 cross 512. If I were to write just one WQ, what would that be? 512 cross 512. 512 cross 512 will take 512 and will give you 512, right? So all 8 heads are now included in there itself. Okay, and that's how you will actually vectorize it, right? So you already have a big hint now. I'll do that if we are left with time, but I don't think so. Yes, so I'm done with this, I'm done with this. Let's start here now. Okay, what is this? I don't understand. Let's start from here. So this is output embeddings, positional encodings. Why do we have output embeddings and input embeddings? Why? See, this paper was written to solve which problem? Translation. So this is for your source language, this is for your target language. Okay. So same thing you do, positional encoding and so on. You start with maybe a start token, because you are supposed to generate things now. And what do? What is masked multi-head attention? So actually decoder looks like encoder, except that here you have masked multi-head attention and here you are receiving things from here. This thing is pretty trivial. This is a little bit non-trivial. I mean, it's trivial, but so what could be masked multi-head attention and why do we need this? एक बात बताओ मेरे को. So we are, so let me just draw encoder here now separately. Sorry, decoder. कॉपी नहीं यार, ये खाली जगह तो मिले मेरे को. यार ये 2 क्लास नहीं झेल सकता है यार. नए वाले भी इतना हेवीली यूज होते हैं क्या? खैर नए वाले ठीक हैं, वो इतना नहीं करेंगे लैग. दिस इज अ 5-year old सिस्टम. अच्छा, okay, so let's start here. I'll do it here. What is masked multi-head attention? See, I start decoding things here. Okay, so this is my just very first layer. I have a start token maybe. This start token is a token in my target language. So I start, right? What should be the output at the all the way until there? What should be the output? Here. What should be the output here of output क्या करने वाले हो finally? So for us, we don't tokenize things right now. We are simply saying output will be a word. Okay, so your output will be a word. So of course, since you are generating the very first token, you don't know anything, so it will be start, right? And but start will give you some actual output in the target language. So output here should be a word in the target language. Okay. So we are here. Start is the input, and then, right? Now tell me, go back to encoder. When you were computing things here, when you were computing self attention here, right? You actually, I should have drawn that as well. So let me draw that as well here somewhere. See, where is this equation coming from? Q1 K1. You have Q1 from here, right? You take dot product with K1. You have Q1 here, you take dot product with K2. You have Q1 here, you take dot product with K3, all the way until K512. This was for your S1 only. In fact, one head of S1, right? What will you do for Q2? Q2 dot K1, Q2 dot K2, K3, K4. Similarly, and so on. So for every output, you are taking inputs from everybody here. For here output, you are taking inputs from everyone here, right? Because you do Qi dot Kj and then finally multiply it with the vector v. Okay, so this is what you have. So everybody here takes input from everybody. Now, what will go wrong if I start doing that here? So I am at the encoder right now. I am at the decoder right now. So if I am at the decoder, this thread, can I make use of this guy? I cannot, because I have not yet generated this. Okay. So when you are decoding things, you can't look into the future. So this was Q1 dot K1, Q1 dot K2, Q1 dot K3, because it is the same thing. If you see, it is masked multi-head attention. So it is that same good old multi-head attention, but it is masked. So what will be the matrix. So how will I do it in this case now? Let us do something that I was not willing to do. Okay, let us vectorize them. How will you vectorize for self attention? We have Q1 all the way until K1 like this. So we have something like, so let's say we have this Q1, then K, I take this dot product, get just one element. So how do I multiply to get this whole vector? You have to help me out. I want this vector as output. Right now all I am getting is just one scalar. I want this vector as output. How should I do things? 5 and 2 एक बार छोड़ दो. Q1 and then what should be here? K2, K3. In fact, let me not draw K3. All the way until K 5 and 2. Will this give me this? Right. So this Q1 is 5 and 2 cross 1. This guy is 5 and 2 cross 5 and 2. I have 5 and 2 in this direction, 5 and 2, 5 and 2 and 5 and 2. Each Ki is 5 and 2. Now you have to tell me, how do I multiply these matrices? Shall I take it this side? Huh? So then this should be transpose then, right? So let us just do what you are saying. So what we simply do is, this is a row. So this is a row, right? And if I make this column, so let me just keep it this way, transpose, right? This is what it is. एक बार देख लो सारे लोग. Because this will now become so K1, K2, K3. This guy is 5 and 2. Which guy? So this is a row vector. Okay, this is row, because if this is row, this is also row, because what I am trying to do here now is, I will have Q1, Q2, Q5 and 2. This is a matrix of size 5 and 2 cross 5 and 2. So this will give me the whole thing for everyone. Okay. Q1 dot this one. So if I am making some dimensional mistake, you guys fix it. Okay. So this is fine. This is QKT. Done. We have that. So this was for just S1. This whole computation will give me for S1 to S5 and 2. This whole thing is a matrix. Here I have something, here I have something, here I have something, and so on. What will happen in masked multi-head attention? So see, these guys, if I take softmax of it, they are going to give me how much should I, so what coefficient will be higher for which values, right? Now what happens in masked multi-head attention? Zeros should be there, right? what should be zeros? यार मन हट नहीं रहा है वहां से, एक बार मेरे को बताना if I'm doing that right, है ना? So tell me, what happens in a yes. So this is my masked multi-head attention. I take this as input, I give this as output, but when I will be doing Q1, K1, this is fine. Q1, K2, is that fine? इधर देखो एक बार, Q1, K2, is that fine for this particular line? No. Q1, K3? No. Right? So this is not fine. What does it mean that this is not fine? We cannot depend on these guys. Okay? Tell me, when we are computing the second thing, is this fine? We will have access to the previous tokens. Is this fine? Yes, but rest all will be. So you have to tell me what kind of matrix is this coming. This first one is Q. What was this? Q1 dot K1, K1. Okay, next one will be Q2, Q2 dot K1 and Q2 dot K2. Next we will have Q3, next we will have Q3, K1, and then we will have Q3, K3, and then dot dot. You will have to tell me what are dot dots. What will be the last row? Q512. So there it will be this guy. This can depend on all of them because it has access to all of them. And this is the autoregressive property. This is ChatGPT. Okay, ChatGPT. If you remove decoder, what remains is ChatGPT. So, I mean, there is a lot more to it, but at the core, this is what it is. So you have how many rows? 512. How many columns? 512. Where are these things coming from? These things are coming from exactly the same matrix provided. कहाँ पे गई वो मैट्रिक्स यार? किधर? ये वाली? राइट में है. Right, this one. Right, this matrix provided I have done it right. एक बार देख लो ना. Q1, K1. So this first row, then Q2, K2, then second. So this is fine. Right? Suppose नहीं आएगा? Okay, whatever it is. Okay, I am not going to that right now. So this same matrix, is this the same matrix? This is the same matrix except this upper triangular should be what? You say 0, I put it 0. What is the problem with 0? These are my attention weights. If attention weights are 0, you will still have zeros there. What will E do? E will take power 0. So E to the power this plus E to the power 1, how many times? 511 times. That means you are still giving weightage to this. This should not be 0. What should this be? This should be minus infinity. because now your weightage on all these guys will be 0, e to the power minus infinity will be 0. So only this guy will have e to the power some quantity, everything else will be e to the power minus infinity, their contribution will be 0 and you will have just dependence on this. Multi-head attention, masked multi-head attention, this is the only difference, else you are done, right. So we are done with this thing as well. अब I am lost कि मैंने बोर्ड में कहाँ पे क्या लिख रखा है. So where is our transformer? This one. So here we have masked multi-head attention is done, okay, because you can't depend on something that you have not yet produced, but you can depend on something that you have already produced in the past, okay. So this is fine. Add and norm I don't need to explain anymore, and we are done with the at least the structure of transformer. What is happening here? What is happening here now? FFNN you understand, this is 512 T048 512, add and norm is that same old thing. What is multi-head attention? In multi-head attention you have queries from decoder, but you have values, or let me first do keys and values from encoder. What will be the output of this encoder actually? Output will be something like, you know, S6 1 all the way until S6 512. If you don't remember what are these, doesn't matter. What we are saying here is the final QKV that were computed at the 6th encoder, they serve here K dot V, right, because for this query you take attention with all these things in the encoder, come up with the probability distribution for the V's of the encoder and then start using here, okay. Questions here. And then finally what happens here? This is good old thing that we have been seeing, right. Softmax will be over my vocabulary size, right. This is that same old linear thing that we have been having, whatever this size may be, okay. And finally you have a softmax over the total number of words or vocabulary. In this paper, that is 37,000 if I remember it right, 37,000, right, 37,000 tokens, but they are tokens, they are not words, but for us right now we will take words, we do not know what is tokenization. I am done with transformers and you still have a few minutes to ask questions. Unless you go through this by hand at least once, right, I do not think you will be able to answer questions in exams. If you go through this twice, there will be no questions that you will not be able to answer. So can I leave my favorite question to you now? Give me the number of parameters in this architecture. So let me see if anything is left or else we are done. So right, one detail was left here, but you guys know it already. So if I have this FFNN, which activation function will be used at T2048 layer? I mean ReLU, right? So you use ReLU in this case, in case of the original transformer. Embeddings are learnt actually, so these 512, right, you learn them, and right, maybe just okay. Now, what does, see, I have just discussed one thing, which is the architecture, how are things connected, right? But you need to read a lot about transformers to see their actual power. So let me just now if you see here, just go through this blog as well. Yes, this is an important thing. So now, no, not this one, this one. So if you have this kind of a statement, the animal, so this is the statement, the animal didn't cross the street because it was too tired. Now if you are using embeddings like word2vec, it will have some embeddings. Word it will have some embeddings. Are they fixed? They will be fixed, right? But now if you see, it actually depends on the context, right? So in this context, so and it will actually refer to nouns, right? So the animal didn't cross the street because it was too tired. So in this case, it refers to the animal. There is yet another noun, which is the street. Okay. Now it turns out that it in our example refers to the animal for one head, too tired for other head, right. So multiple heads help you contextualize things. It was otherwise just it, but right now in this case it will have embeddings closer to the animal and tired in green space here, in red space here. So if you see in red space, it focuses too much on the animal. So when you look at that distribution, that probability distribution, it is focusing on these two words because it actually refers to that. But who was tired again? So another multi-head, so you had 8 heads. One head is taking care of the animal, another head is actually referring to the tired. So what these guys, I mean, we have not talked about the interpretations of transformer at all, right? But what happens, they contextualize your embeddings. So when you do this 6 times, self attention, self attention, self attention, the final vectors that you have, right, they know a lot about the input sentence. Maybe we will talk about this in the next class. Okay. So that's it for today.